Hello, everyone. Hi, I'm Remi. I'm the founder of Inco. Today, I'll be talking about confidential ERC20 framework. It's a new primitive for on-chain confidentiality. So this is from a report from Paradigm. So they interviewed over 300 institutions. And if you see here on the charts, the lack of privacy is really one of the top 3 reasons why institutions are still not using DeFi and blockchain today. The first 2 reasons are really around perceived risk and regulatory uncertainty. And privacy here, as we can see, is pretty much on par as the first 2 reasons. So this is the current status of today's blockchain, right? So everything is transparent. Your address, the amount that you hold, and how much you're sending to each other. Now, blockchain transparency really is what we think is the feature, right? Because you want to be able to verify that nobody's cheating, there's no double spending. But really, it's more of a bug than a feature. Why do I say this? Because how can you actually adopt blockchain technology if everything on chain is fully transparent? So by show of hands here, who uses crypto every day here? Or has some crypto, right? The truth is, like, you can see how much everyone has, what everyone's buying, what everyone's trading. If we were to onboard 1 billion people today, wouldn't this be crazy? Like, you can see how much your neighbors has, how much you're getting paid, etc., right? So really, privacy is going to be necessary for mainstream adoption. And the reason why so far it has not been incorporated into blockchains is because we haven't had a really good way to make it verifiable, right? So we should really think about privacy also as a spectrum. So a lot of people think privacy is just general privacy, but privacy should really be seen as a spectrum. So on one side you have confidentiality, and then on the other side you have anonymity. So what is anonymity? The idea is really you want to break the linkage between the sender and recipient. So by doing so, you're actually kind of hiding how much everyone has, but also the addresses, right? So this is just obviously a rough generalization, but the key point of anonymity is that you want to hide basically who's interacting with whom. And so what are some practical examples of use cases of why you need anonymity? So what if you were to visit a medical facility, right? If you were to see a doctor, you probably don't want this information to be on chain. Or what if you need to give a political donation to either party, you probably don't want this information to be on chain. And so there are a couple of projects that are working on anonymity, such as Solana Cash, Railgun, ASEC. And again, this visual representation is obviously not going to apply to all these projects, but the idea is that you want to break the linkage between the sender and recipient to achieve these use cases. And so what is confidentiality? So confidentiality is the more vanilla version of privacy. The idea here is that you want to hide the amount that people have. So I could look on chain and see that this is Alice's address, this is Bava's address, but I cannot see their balance. Their balance will be encrypted. But you can still send a confidential amount to each other. So it's very similar to like a Venmo experience for those from the US, or like a Revolut. You can see your friends sending money to each other, just not the amount. And so what are some practical examples of use cases for confidentiality? So payroll. Right, so you want to hide how much you're sending to your employees, how much everyone's making, or supply chain. So the classical example here is Coca-Cola. We all know who the suppliers are. We just want to hide the amount that's being paid out, right? So this is a really good use case for confidentiality. And some example projects that utilize confidentiality include Solana confidential transfers, Avalanche ERC20, and also confidential tokens that we're proposing here. So why is this such a difficult topic, right? The reason why is because privacy can be problematic, right? Hackers actually love to use privacy to launder their funds, as we've seen. So there needs to be some kind of compliance in place to avoid this type of issues. On the other hand, actually compliance actually can also help bring privacy to mainstream. If you think about things like payroll, there's a lot of PII information be involved. So at some point, today, most people don't really care that you're sending, payroll over on-chain in a public manner. But in many ways, this is actually a very gray area and actually very problematic down the line because you are actually leaking a lot of PI information. So as this space matures, compliance will actually help push for privacy on-chain and advocate for it. So there are a lot of existing privacy solutions that are commitment-based. So Tornado Cash, which is probably the most famous one, is essentially a mixer, so you're able to break the linkage between the sender and recipient. Zcash is a privacy chain. It doesn't have smart contract capabilities, and there are projects that have been trying to apply compliance to ZK-based approach, such as privacy pool. So the idea of privacy pools is very similar to like a tornado cache, but the difference is every time you withdraw funds, you can generate ZK proof that any address that are blacklisted or malicious are not sending funds to you, right? So you're basically sort of proving that you're innocent, or the funds you're withdrawing are sort of innocent. And then CAPE is another project that uses also a commitment-based approach. The way they do compliance is by enabling some kind of viewing key that can be shared with auditors. So what we're proposing here with the confidential ERC20 essentially is a encryption-based approach. So what I mean by that is basically think of MPC, FHE, TE. I'll say it's a different category of solutions than the other side, which is ZK-based solutions. And the confidential ERC20 framework is actually very similar to a regular ERC20. It has all the similar features, so you can see your balance, you can send money to each other, you can do transfers, you can do allowances. The reason why we're not saying it's directly the same is because we do have to change the data types. So obviously the fields of your balances, the amount you're transferring are going to be encrypted. So that's why it's actually not directly the same. But you can actually turn this into a wrapper. So in that sense, you can basically turn any ERC20 into a confidential token. So if I send USDC to this wrapper, it becomes a confidential USDC, or if I send USDT, then it becomes a confidential USDT. And this can also be extended to add additional rules that I'll cover later, things like transfer rules or block lists. And there are two things that also can be optional. So one is delegated viewing, and the other one is transfer rules that I'll cover in a bit. So in the paper, we basically use FHE as an example. So what is FHE? FHE essentially stands for fully homomorphic encryption. The idea is that you can encrypt information, but also compute on top of it without having to decrypt. So imagine if I were to encrypt the integer 10 and someone else encrypt the integer 2, we can both basically add the two together without revealing information. And when you decrypt, it actually becomes 12. Sounds like magic, right? So decryption is actually decoupled. So typically the way FHE works is, you use cryptography to do compute, but you're also using different type of cryptography. Well, you could use MPC basically essentially to decrypt. So these two, you can think of it as decoupled. And the scheme that we utilize as an example is TFHE, so it stands for FHE over Torus. Why FHE over Torus? So there are actually many different FHE schemes. FHE over Torus essentially has a couple of properties that are quite useful in the smart contract context. So one is the accuracy of computation, so the end results will always be accurate. And the second is it does support a quite range of operations, such as additions, divisions, multiplications, etc. And also non-level, so meaning that you can keep on computing. And the reason why this makes sense in the context of smart contract is because you don't necessarily know ahead of time how many steps you're going to be computing, right? So you want something that's actually non-level in that sense. So you can apply FHE to the EVM in a couple manners. So basically, obviously, as a native chain, when you add this as a precompile, the second way is really as a coprocessor. So this will be enabling FHE to existing blockchains. And by doing so, you essentially enable new data types inside the EVM, as well as compute capabilities. A couple trust assumptions that are worth mentioning. So ZK FHE today is still quite expensive and kind of far away. To give you some sense, a bootstrap takes roughly 20 minutes to prove. A multiplication will probably take something like 20 days because it has a couple thousand bootstraps. So that's probably some time away here. You can also come up with some kind of optimistic fraud proof where, similar to your typical rollup fraud proof, you can do some kind of bisection, right? Or this third way is really via consensus. So because it's deterministic, you can have different nodes perform the same computation, achieve consensus, and so that's one other way to basically you can do it today, but obviously at a cost, right, of replication. The decryption is going to be MPC based, so the trust assumption here is M of N. You really have to trust basically the folks running the MPC network. But just wanted to explain how this looks like, how the confidential token looks like in practice in terms of code. So with these new data types, EUINTs, you basically can hide your balance, right? It's an encrypted balance. And when you do a confidential token transfer, essentially you're passing in an encrypted amount as a parameter. And then in the first line of code, you basically check if the amount you're transferring is less than your balance, right? And from that, you get an encrypted Boolean, which basically you pass into the second line. A select function, you can think of if you're a developer, you can think of it kind of like a ternary. Essentially, you pass in as the input and it returns the first argument, the amount if it's true. And the second argument is 0, but 0 is also encrypted. So essentially, the transfer value here on the second line could either be 0 or the actual amount, depending whether or not the first line is true or false. And what you end up doing after is you're adding basically this amount to both the sender. So you're adding the amount to the recipient, and you're subtracting from the sender. So you basically end up adding basically the actual amount or adding 0 or subtracting 0. And the reason why this is designed in such a way is because if you think about it, right, if it's a public blockchain, the validators can run a node, you can view everything that's happening on chain. How do you write conditionals, right? You can't have conditionals because if you basically execute different path, you are kind of leaking information about how much the user has, right? So this is actually one way to overcome this problem. And then to allow for view functions, you basically have something a little bit more explicit. I can allow different parties to view my balance by calling this allow function. So just a quick demo on what this looks like. So this is on base Sepolia. You can send USDC to the wrapper contract. So here I'm basically shielding an encrypted amount. Actually, sorry. The amount I'm shielding is actually public, right? Because you are sending plain text token into the wrapper. Now, to view my balance, all I have to do is send an EIP712 message to prove that I'm the owner of the wallet. And then I can send a confidential amount to another party here. And so here, the number 5 is actually encrypted on the client side. And I'm just casting a transaction on the client side here. And let's take a look at the Etherscan. So we can see that I'm interacting with the contract, the wrapper contract. The address is transparent. And the amount here is what's encrypted. After, yeah. So in the paper, we really compared, I would say, 2 categories of solutions, like I mentioned earlier. One is commitment-based solutions, so think of ZK. The other one is encryption-based solutions, so MPC, FHETE. And there are differentiated properties here. So we can argue that commitment-based solutions are actually more scalable as we go because everything you prove is on the client side, right? So you're kind of distributing the work across all the users. In the encryption-based solutions, you kind of need the blockchain, all the co-processor perform all the work. So it's a different type of scaling challenges. But there are also other trade-offs here. You can also argue that commitment-based solutions are also more private because the secret key that's used to encrypt your balance never leaves the client, right? In the encryption-based system, it's actually a shared key. So you could argue that it's a little bit less private. But in terms of the encryption rules, encryption-based systems are going to be a lot more flexible as compared to commitment-based solutions. So I'll dive a little bit deeper here on the next slide. And then the last part is really around this idea of composability, which is also quite of a differentiated property that encryption-based solutions offer. So why is commitment-based approach more rigid, right? It's more rigid because every single user has their own viewing key. And so typically the challenge with that is you need to install a new wallet or find a way to custody this viewing key as an additional requirement. When Bob sends money to Alice, Bob has to specify Alice's viewing key part of the proof generation. And so only Alice can view her own balance at the end of the day. But what if she needs to do taxes, right? Or what if she needs to delegate viewing to an auditor, to an exchange, to chain analysis? This becomes very rigid because they wouldn't have access to Alice's viewing key unless she explicitly give the viewing key, which obviously is problematic because then they can see everything. In the encryption-based approach, because it's a shared key, what ends up happening is that all the decryption rules can be fully on-chain. And so you can always change these rules via transaction, governance, in various ways. And you also don't need a new wallet, right? Because there's no viewing key requirement. You can also retroactively always audit, investigate backwards, right? Versus the commitment-based approach, you kind of have to know who gets to decrypt ahead of time. So it's very different paradigm, I'll say, in terms of like flexibility. And there are practical reasons why you want maximum flexibility for decryption. So for example, if you a user, obviously you now want to delegate viewing to your CPA, accountant to your taxes. If you are, I would say, an asset issuer, maybe you don't want to monitor the asset lifecycle, the velocity of confidential USDC, for example, being transacted. If you're a government entity, maybe you can enforce some kind of like compliance monitoring, etc. There are a couple benefits here with composability. So one is end-to-end confidentiality. So there are a few projects working on dark pools. The idea is that they want to enable some kind of private trading. Now, the problem with dark pools generally that most people don't know is that you are already leaking information the moment you send money into the dark pool, right? Because everything is transparent. Now, if you can send a confidential amount to a dark pool, then that already reduces a lot of the risk and the typical like reactions that people will have. The second part is composability over this idea of a shared private states. So what I mean by that is the confidential token is actually very similar to like an ERC20. Today, if you look at Uniswap, Aave, Compound, we're all using the same primitive and then building on top of it, kind of like a Lego, right? So confidential tokens also have the similar property where I can extend the confidential token to build a streaming payments application, governance, lending, etc. So what this really means is that you can actually keep on expanding and creating some kind of network effect with different applications on top of this new primitive. And this is not going to work with a commitment-based approach because of this viewing key requirements, right? It's just adding a lot more complexity because things happen off-chain. So one example that is quite interesting with this idea of composability is that you can program transfer rules. So we've done some work with the Tokeny folks on the confidential ERC3643. The idea is that you can have a confidential identity module where imagine storing user credit score, age, geographic location, encrypted manner, and you can still program transfer rules without revealing what it is, right? So for example, if Bob and Alice are not from the same jurisdiction, you can basically essentially know the transaction, you basically end up transferring 0. Or there are all sorts of basically rules that you could program based on this on-chain identity that's fully confidential. And so the confidential token really is a new primitive that's quite useful for various use cases, including payments, cross-border payments, token vesting. So imagine, vesting your Arbitrum tokens, Wormhome tokens, or any tokens for payroll, for remittance, and then the idea is to also enable new use cases, primitives to be built on top of it. Just wanted to quickly compare confidential tokens, commitment versus encryption-based approach. So like I mentioned earlier, there are a couple different parties offering confidentiality via confidential tokens. So by having a shared viewing key, you essentially are going to be more compatible with existing wallets and tools because you don't have that extra requirement. You can program basically decryption rules in a more flexible manner. It has a lower cost because there's no ZK proof verification, and then it is composable, so you'll be able to extend this token with more use cases. Versus a commitment-based approach where every single user has an individual key, you are going to need some kind of new wallet or new ways to store this additional components. The decryption rules are going to be a little bit more rigid because you have to know ahead of time who gets to decrypt. And then there's typically a higher cost as well because of the ZK proof verification. And then lastly, it does prevent composability. So typically, folks will use these tokens to just purely do payments. Just want to conclude saying that the idea really of the confidential ERC20 is to propose a new primitive that's more ergonomic to program in a business logic, risk management, compliance, in a friendly way. And the second part is really just enabling folks to program more things on top of these new primitives. So we're happy to chat with you if you're interested in learning more about this. And I'll take some questions now. Yeah, go ahead.
Is the confidential ERC framework specific to FHE, for example, or to the underlying scheme?
It's a really good question. No. So this is what I meant before. We can think of two categories: commitment-based solutions, which are typically ZK, encryption-based solutions, so MPC, FHE, TE, all can achieve the same property, basically. Yeah.
If I understand correctly, I would be able to see the ciphertext of balances. Is that right? And if so, if I have one token in my wallet and you have one token in my wallet, is it the same ciphertext or a different one?
So that's a good question. So no, the answer is no. There's always some randomness added to the ciphertext. So even if you're encrypting the same integer, you will look differently from the outside. Yeah.
So speaking of base topology demo, you said that the amount is the encrypted data and the address is a plain text. Why not make the address is encrypted as well? Is it the legal requirement or something?
So that was kind of like the spectrum that I showed earlier. It's good for a different use case, right? You could also encrypt addresses, but it would be for a different use case. And so I didn't show it for this presentation, but in my previous presentation at Stable Summit, I also kind of explained how to think about compliance, right, around this spectrum. So obviously, yeah, if you're offering something more vanilla privacy, like confidentiality, the risks are going to be a lot lower because it would be a terrible tool for money laundering, right? If all the flow of funds are traceable, not really great for money laundering. If you're offering anonymity, this is where you have the most risk. You have Lazarus who might use it, et cetera, right? So this is where ideally you want to enforce a little bit more compliance, KYC, KYB, everyone, if you can. I think that part is definitely a little bit more problematic, and it's also not super clear what is the right approach, and I think everyone's trying to figure out, basically, yeah.